discuss the findings of one project, the compressive strength of high strength concrete modified with synthetic fibers and limited integration. This project is advised by Dr. Hawileh and advised by Jamal. A quick overview of our importance. We're going to start with a quick introduction to the project, moving into our problem statement, then we're going to discuss our methodology, then present our experimental results, discussion and analysis of these results, to our complete final recommendations. Starting with the introduction. First, let's define what's high strength concrete. High strength concrete is a brittle material formulated by combining normal Portland cement with a combination of supplementary cementitious materials, and usually it combines a combination of extremely fine aggregate and small sized coarse aggregate. High strength concrete is extremely brittle, so for this experiment to obtain acceptable ductility, we decided to introduce steel fiber to the mix. The properties of the concrete mix that we have used is, first of all, it had an extremely high density. Second, its residual strength was extremely high, and that was due to the addition of steel fibers. It was highly ductile, and that was also due to the addition of steel fibers. Its tensile strength exceeded that 15 megapascal, actually it reached around 230 megapascal. Its compressive strength was approximately around 100 megapascals with few variations. In a quick comparison between normal stress concrete versus our concrete, you can see the following. First of all, normal concrete is extremely brittle while our materials is extremely ductile. Normal concrete is also permeable while our material is extremely dense. And finally, normal stress concrete is has extremely low residual strength while our concrete is extremely high. If you want to take numbers into account as presented, the normal average compressive strength of normal strength concrete is around 40 megapascals, while for us it reaches 200. The normal tensile strength, which is around 10%, it would be assumed up to 5 megapascals, while ours exceeds 15 or even higher. The flexural strength is usually 6 megapascals for normal stress concrete. However, for us, it's reached up to 40 megapascals. Now, the big problem that faces high strength concrete, especially with the addition of steel fibers, is explosive spalling. Explosive spalling is a violent expulsion of the fragments caused by the rapid stress development inside of the concrete figures. In other words, when the concrete is too dense, the stresses start to develop inside the concrete, which is at elevated temperatures, causes the concrete cover to explode. This figure over here presents one of the samples that face explosive spalling from our testing. As you can see, the sample is totally deteriorated, and the concrete cover has totally disappeared, and only the steel fibers are clearly seen. For this problem, our research showed that using polypropylene synthetic fibers prevents spalling and could have some effects on the mechanical properties of the concrete. To further understand the effect of polypropylene and explosive spalling, a study done by Nanyang Technology University explains the role that polypropylene fibers plays in the reduction of explosive spalling. The polypropylene fibers work by bridging the cracks and the pores inside the concrete when they melt at a high temperature. When they do so, the vapor pressure that's caused by the water inside the concrete evaporating away and causing internal stress inside of the concrete starts to dissipate through these channels that are presented by the polypropylene fibers. When this pressure escapes out of the concrete, it eliminates the risk of explosive spalling. Now, that brings us to a problem statement. A problem statement is as follows. First of all, was the extremely high brittleness of high strength concrete, causing sudden and uncontrolled failures. This was fixed using the steel fibers that we have introduced to the mixed design. The second problem statement is explosive spalling acting as a limitation of high stress concrete in rigid structural elements. In other words, if you want to use high stress concrete building columns and core walls, the risk of explosive spalling would cause many developers and contractors to reconsider their choice of concrete. Now, moving forward to our methodology. First of all, the first step of our methodology was getting our mixed designs. This experiment was conducted with two mixed designs. The first one was high strength concrete with steel fibers, and the second was high strength concrete with steel fibers and polypropylene. As presented, the following is our mixed design. Our cementitious content composed of 63% quaternary carbon 7 top C, 11% silica fumes, and 26% GGBS. Our water cement ratio was approximately 2.9, and the steel fibers occupied 1% of volume. This value was obtained with consultation with experts in the field. Polypropylene fiber content was said to be 0.1% of volume, and similar to the steel fibers, this value was set based on our consultations with experts in the field. Moving forward, we prepared our testing samples. 40 of standard cylinders were casted for this experiment. The third step was testing the compressive strengths. Six of these cylinders were tested at the room temperature to get an average of the compressive strengths of the concrete and the room temperature. The samples were tested according to the ASTM C39, and they were also capped using the ASTM C617 to ensure uniform load over the samples. These testings were done on our SANS compressive testing machine, which was presented in the figure. Moving to the next step. These cylinders were mixed. A total of 6 compression cylinders were tested at elevated temperature. Now moving on to the experimental results, starting with our high strength steel fibers blocks. We could start it with 90 megapascal compressive strength in room temperature and an average of 88 to 89 megapascal compressive strength that was maintained as we went to 200 and 400 degrees Celsius. However, since the severity of explosive spalling caused a dramatic increase and the compressive strength of the concrete falling to as low as 28.2 megapascals, almost a 70% reduction in the compressive strengths. When we present the mass loss, as observed in the figure, there was an extremely high mass loss and reduction in concrete cover caused by the explosive spalling, the normal loss of concrete cover at elevated temperature caused by the shrinkage of the cement base. The following figures present the severity of explosive spalling and the damages that it made to the concrete. Now, however, when we shift the results to the high strength steel fiber polypropylene mixed design, we could see that at 25 to 100 and 400 degrees, the results are similar to that of the high strength steel fiber mixed design. However, at 600 degrees is when we start to see the effect of polypropylene fibers. As presented, we only dropped to 76 megapascals compared to the 28 megapascals that were achieved at the steel design on mixed design. Steel fibers on mixed design. When we present the mass loss values, we could see that we are only achieving 3.8% maximum mass loss. This mass loss is due to the failure of concrete cover and evaporation of water from the concrete that's caused by the exposure to elevated temperature. The following figures present the samples after being exposed to 700 degrees Celsius. Now, moving on to the discussion and analysis of results, we'll start off with the effects of temperature on masses as presented. The polypropylene steel fiber mix design had an extremely lower masses compared to that of the steel-only mix design. However, both of them showed a linear relationship and the reduction of mass with increase in temperature. Now, to compare our results to that of normal stress concrete, we have obtained the strength reduction factors from the Eurocode 1.2, and we set our results to compare with the Eurocode. The Eurocode, as presented with the blue figure, shows a uniform reduction in strength with an increase in temperature. When you compare the steel-only fiber, we could see that at 600 degrees, we're achieving results that's extremely lower than that of the Eurocode, almost 25% reduction factor, while the Eurocode is achieving around 45%. While if we observe the steel fiber polypropylene mix design, we're reaching up to 82% or 84% as a reduction factor for our high strength polypropylene mix design. Moving into our conclusion, first, we could see that there's a linear relationship established between the temperature increase and the mass loss, with our high strength steel polypropylene mix design showing the least mass losses compared to our high strength concrete steel fiber only mix design. Now, we could also see that there is a continuous decrease in the compressive strength of mix designs with the increase in temperature. However, we can also see that decrease in strength is reduced. Polypropylene fibers added. Third, the study proved that the additional polypropylene fibers had no significant effect on compressive strength of temperature, despite some papers and research showed that the additional polypropylene has a negative effect on the compressive strength of the concrete. Finally, the study proves that polypropylene fibers are effective in resisting explosive spalling at elevated temperatures, hence achieving our goal of solving our problem state, which is allowing high-tech concrete to be safely used as major structural elements in residential and commercial buildings. And with that, we reach the end of our presentation.